ESG section. Here. So that provides the portion or why and X. This just provides Y.
I love the first two.
Well, it's the same thing. So did you find the reaction input to the B? Okay, so once I found the reaction input to the B, I just found everything with everything so right here. So that's where I found the actual working. Like this something. This.
Very exciting. You guys have a good weekend? Brian, what do you do in the summertime? Kids to keep them moderately safe. Yeah. That's a good move. That's a pro tip right there. Sounds lovely. Oh, nice. Get the sponsor on there. Be sponsored by Rain on the end of that. Let me see. Today's no good. Tomorrow. I'm on it. I'm on it. What's up?
This one I'm gonna get rid of the fast like that. Actually, I think this one I will. And I want to know like what toxicity gives you the fast. There's different heights too, like this one can be 1.3 meters.
I think you fulfilled the requirement. So like, you're not testing the same thing. You're testing the same types of numbers, which is fine, but your distances and your angles are different. So
This is the next part of that.
Sure. Sure, you can ask. Okay. So you're putting a distributed load across the beam. So the problem is once you apply a distributed load, it's no longer a truss. So if you're using truss members, you're violating the truss, right? Because once we apply, if the forces do not, so applying a distributed load isn't the problem. Applying a distributed load that doesn't get applied at the thing is a problem. Yes. Sure. No problem. 2 minutes, guys. I always think of it as the moment always curves in towards my section. Yeah, so yeah, essentially, right? Because those are the equal opposite. So the moment always curves up, and for the shear, right? In order to balance that moment, you have to bend the beam the other way. Right? But when you do enough of them, but when you just start it seems arbitrary, right? And to a certain extent, I think that it is. It doesn't really matter as long. The thing that's important is if you were to separate both equal and opposite, because the math will work it out. Sure. Yeah, they have. It's nice. From my perspective, that you guys do some work there. It's not nice because you don't get like quality feedback. Oh, it's 11 o'clock. We're gonna get started. Back at it, doing the statics again here in room 123. I don't know. We're here somewhere doing statics. Hey, say hi to Katya and Kat, everybody, and Dr. Roland. They're gonna sit in today and explain why there's chemistry on the board. All right, let's get started. Lord, thank you so much for bringing us together and for everything that you do for us. Thank you for this weekend and hopefully allowing us to get some space and to rest and relax. Pray that you would continue to help us with everything that we need for this semester. Help us to stay strong, stay in it, and not get discouraged. In your name we pray. Amen. All right. Hope everybody had a good weekend. If not, re-examine what you did and then do something different the next time one comes around. Anyway, we're going to go over the quest. I did not finish grading them yet. Not even close. They'll get done by the end of this week, just like the last ones. They kind of take as long as they take. They'll be as close to 1 week as possible. It just really depends. Then we're going to recap from last week about internal loadings. And then we're going to jump right into beams and bending moment and shear and bending moment diagrams specifically, because I'm sure you have a bunch of questions from the homework that say draw this shear and bending moment diagram, and you're probably like, that's great, but nobody told me how to do that yet. So I'm going to tell you how to do that. All right, first thing, here is this thing. It's a socket, or it's a socket wrench, right? The socket exists. All right, we have a 20 Newton force that's being applied here. Some people asked, is that just in the XY plane? It is intended to be in the XY plane only. You know that because you're not really, I guess the way you look at it, maybe that's in the YZ plane, but that's not really how we would use this, right? If I was to pull down on the handle in the YZ plane, right, that doesn't really help me to loosen the bolt in any way, right? So that's a thing. We need to find the magnitude and direction of the moment. That's a fancy way of me asking you to give me the moment vector, right? I need the vector, right? Okay, so worth 20 points. This one was supposed to be pretty quick hitter. All right, so what do we know? Well, we know we have 20 newtons. No, 20 newtons at 60 degrees off the y-axis. Okay. And we know the distances, right? We can put that in there. Those are going to be important in a second, depending on how you chose to do the problem. There was a bonus 5 points if you did it a second way. So this is not an equilibrium analysis problem. This is just find the moment. Find the moment about point O, right? So what are we asked to find? You guessed it, the moment about point O. All right, it says to draw a free body diagram. I guess we'll do that because we're always doing that because it's everybody's favorite. Here is a very fancy free body diagram for this particular system. I guess I have to put a little bit of depth on that, right? So we'll make it look kind of like that. Okay. This has a thickness of 10 millimeters, right? I did not specify whether you were supposed to do this in, Newton meter or Newton millimeter, right? And so you choose whatever you want. Degrees off the y-axis, that's 10 millimeters thick. We're also told the length of this, right? The length of that bar was 200 millimeters. And it was 50 millimeters tall. There we go. And that's our free body diagram. Here's something interesting. How do we find the moment of about a point? How do we find the moment about a point? Well, the easy way for this one, in my opinion, is to do this. Cross product. We have the force vector, or we can create it as best as we can, and we have everything we need to make the distance vector, right? The other thing you could do is go at it from each of the planes and figure out what components of that force create a moment about the x-axis, about the y-axis, and about the z-axis. It's the other way we can do it, and that works too. Just depends on how you want to do it, right? And you were not instructed for doing it a specific way, so just need to be one of those two. All right, so if I'm going to do it that way, I need R, let's call it O to A, because this was given as point A, and that's point O, which means I've got some vector that takes me there that we're going to call ROA. And ROA in the x direction is negative, right? Because even though I didn't label them, in my brain they were labeled. And here, that's what they look like. Okay, so the x direction, we actually have to go negative 0.01, because I did it in meters, right? For no other reason than to just do it in meters. I don't like the way that Newton millimeters looks when I report units, so sue me. But if you use Newton millimeter, good for you, doesn't matter. All right, negative 0.01 in the I, plus 2.2 in the J, plus 0.05 in the K, and like I said, that was in meters. Okay, great, force vector. We were told that this is in the XY plane. We're shown that it was. So this is going to be what? This is going to be 20 sine of 60 degrees in the J. Look, it's pointing towards us. It's pointing in the positive direction. The way that this is set up, if you're looking at it in the XY plane, right, the vertical, right, is the X direction. not the horizontal, the opposite from that angle. Remember, it's always from the angle that we're using. And I don't know why I wrote J, that should say I. Because I want to confuse everybody so much that they leave here and they don't know what I'm talking about. Great, mission accomplished. There we go. And these will all be in Newton. Perfect. Well, there we have it. Okay. So that's our two vectors. Now we just need to do a cross product. It'd also be 0 in the K, which I didn't put on there, but it's implied since I didn't put anything there. And typically when I don't report something, that is synonymous with it being 0. So if we go to do our cross product, right, just draw my IJK circle. I get what? Well, I'm going to write out my vectors and we're going to do this guy. Negative 0.01, 0.2, 0.05, cross 20 sine of 60. If you did that out, it would be 17.32, roughly. Cosine of 60 is 1/2, so this is negative 10. And like I said, 0 in the z direction. Great, so now we just do our cross product, right? So if we're looking at the I direction component, right, I cover up my first column. Don't really want to do the thing, but I'll do the thing anyway. All right, so remember, I cover those and I just deal with these, right? So that's going to be 0.2 times 0, which is 0, minus negative 10 times 0.05, which is 0.5, right? Because minus a negative gives me a positive. And so there we have it. If I'm going J into K leaves my I positive, and so there it is. All right, J. Now we'll do the J version. I'm going to leave the sign off for a second. In the J direction, I cross those out. I get 0 minus 0.05 times 17.32. That one I'm going to need some space because I got to write that out. And the J. J gives me I cross K, right? I cross K, I have to go backwards around here, go this way, and apparently pull up the next problem, which is also convenient, which is negative, right? So this is going to be negative here. But if you notice, this will be minus a negative, right? So it's going to come out positive at the end of the day. Do the same thing for K here. We cross those. Here's my K. And this, just so we're all aware, in my version is in Newton meters. Yours might have been Newton millimeters, which is, as I said earlier, perfectly fine. Negative 0.01 times negative 10 minus 17.32 times 0.2. There. In the K. So good. All right, let's punch this out. We got 0.5i plus 0.866 j minus 3.364 in the K. And there we have it, the magnitude and the direction of the moment vector, right? If you wanted to, you could be a glutton for punishment and find the magnitude and the angle. I don't know why you would do that to yourself, but you could have. I would not have done that. I would have left it like this. This is perfectly good, but there it is. And you just had to do the cross products. Now, you're asked to check it if you were asked to check it, right? Well, we weren't asked to check it. If you wanted extra 5 points, you could check it. How are you supposed to check it? Well, we'll go over that in a second. Does anyone have any questions about this before we go through the check? I'll leave this up here. No questions? Okay, cool. Let's get rid of this, because we don't really need any of these things anymore. I'll leave R and F up there though. This is a good reminder. So what are we going to do? Well, the first thing that I did if I wanted to check this is I need to draw a new free body diagram, and that one's going to show me the XY plane. And if I'm looking in the XY plane and I have my bar, it looks like this from the top, right? Where looks kind of like that from the top. Well, let's do it the correct way. It looks like this from the top on this side of the bar, right? And we know that this thickness here is 0.01 meters, and we have some force, and if I was to look at this here, right, this would be 60 degrees and 20 newtons. And that's the whole thing in the XY plane, right? It's weird because X is positive downward, right? But that's fine. So we can determine the moment here, right? We also have one more distance that's completely relevant here, right? And that's our 0.2 meters across the bar. I can break this down into two pieces, into an X component and a Y component. Because of the offset from the Y axis, both of these have a moment contributing about O in the Z direction, right? Everybody sees that? It's a small one from the X component, right? Because it's 10 millimeters, right? It's not a huge amount, but it's still there. So we're going to account for it. So if I want the moment here, this will be the moment about, O in the Z direction, okay? And it's really the sum of the moments about O. Like, in order to get the resultant moment, we just add up all the moments that occur here, right? And so what do we end up with? Well, 10 times 0.01, right? That's our 10 newtons from our Y force, which is applied 0.01 away from the Y axis, right? And then we have 17.32, right? Minus 17.32 times 0.2. This looks really similar to that part of the cross product that we just did, right? Because it's the same part of it. This is what the cross product does. How did I determine this? Well, all right, let's take a step back. What if instead of having that, I decided to draw this as, I know this is 17.32 because I've calculated it over here, and I know that this is 10, and they're both new, right? So 10 is going to push, this is here like this, and I push 10, goes in the counterclockwise direction as positive, whereas 17.32 drives us in the clockwise direction, which would make it negative, which is why we have this. And turns out that if we do the math, we get 3.364 negative. Hey, so far so good. It checks, right? So that's our Z component. Rinse and repeat in the other directions. The nice thing about the other directions is there's really only one force if we view this in the opposite direction, in the other planes, right? Why? Because there's no Z direction component in any of these planes, right? So we just deal with the X component and the Y component as we move forward. So for our next one, we'll look at the XZ for reasons. Doesn't really matter. But here we go. That's our thing. Here's 0.0. Here is, just for completeness, X and Z. And if you were to look at this in, sorry, I'm looking at, I drew that wrong. I was looking at the wrong figure. Let's try that again. So if I'm going to look at this in the YZ plane, here's 0.0. Here's Z. Here's X, right? You're looking at it straight down the handle. What is this going to look like to you? It's going to look roughly like there's some there's 2 points, like right there, like that, with like, oh, there. Yeah, something like that, maybe. Looks like a block with a force at the top. The Y force is going into the board, so that's not going to create a moment about the Z. So we're just left with our 17.32 newtons. All right. Great. Where is this? This is applied at 0.05 meters from O. So moment in the Y direction is equal to 17.32 times 0.05, which is 0.866 Newton meter. Great success, matches our J direction, which is what we would expect if this is going to rotate about the J axis. Okay, and then the last one is the ZY plane. Point O, if we're looking at this in the ZY plane, this looks like this. Guess what? The distance is still 0.05. And we're just dealing at that point with a 10 Newton force. Moment in the X is 10 times 0.05. That rotates clockwise direction. And so we have it there. And now we end up with 0.5 Newton meters. That's in the I direction. So then we've checked it, it works out. If you had done it this way instead of the other way that I did it for your main part, that's fine. You have to put it all together. You have to tell me which one's I, which one's J, which one's K, right? You have to write the vector out. That was the whole point of asking for the vector. But there it is. All checked. It's good to go. Okay. Any questions on this? Jane? No, in these, you've already found it because this is in the X direction, this is in the Y direction, and this is in the Z. So you just, when we're doing the check, we're basically making sure that we're finding the different components, right? If you were to do this in reverse and try it this way, then yes, you have to write down, you know, this is I direction, and I'm going to try this with the mouse, right? Ooh, pen is definitely better, but if you thought my handwriting couldn't get worse, there you go. Nailed it. Challenge accepted. All right. Cool. Any other questions? All right. Now for the main event. Main event. This guy. What the heck, Dr. D? Yep. How do you sleep at night? All those things, right? I get it. Right. Okay. Now you guys, you're not gonna believe it, but there's an easier way to do this than what you're thinking. So here it is, right? Determine the reaction forces and the forces in all the members. Make sure to list which members are in tension and are in compression. Send the results in. I didn't get any emails, so bummer for you guys. Just kidding. That was a joke. It's horrible. Why would you say that? All right. Bonus, check your work, right? Notice that the bonus is also to check your work. That's crazy. Okay. So, knowns. All right, let's get to it. The knowns are the applied forces and the distances, or dimensions, or however you want to say it. Find the reactions and forces in all members. Oh, we're done. in all members. Okay, great. So we're asked to find the reactions. First thing we need to do is draw free body diagram for the entire thing. Before we do that, I would like to go back and show you the actual picture of this. This is a very interesting structure. Why? Because it is symmetric. All of the dimensions are symmetric, right? It's also loaded purely symmetrically. So you only have to solve half of it. And then you can copy, then you know that the forces are the same on the other half. That was the trick. You could brute force your way through this. You could. And that would take a lot of time. And that was not the intention. But symmetry was our friend here. Let's work it out though. A to H, right? There. I know, you're so mean. I hate you, all that. I got it. Understood. Picking up what you're putting down, all that stuff. Okay. You don't sound like you care. I do. I care terribly. That's the problem. I care too much. That's what you should definitely say when you go to your job interviews. What's your weakness? I care too much. I think that's all of them. Yep, that's all of them. All right. Let's label these because that might sound like a good idea. This is going to be AY, this is going to be HY, this is going to be HX. The rest of them are in pounds. Yes, yes. I almost put kips down. That would have ruined ruined my day. Use kips. Okay. Couple things here. We can label all of our joints. Mm. And there's some dimensions. All of these are 8 feet across, right? This first part up to here is 6 feet, which is nice because then you know all of those lower triangles are 3, 4, 5s, right? So we know that these are 3, 4, 5 triangles on every one. Couple of things just to note right off the bat, right? If you're looking at it, CB and GF are both zero force members. Those are the only two zero force members in there. And you're going to be like, well, hold on, Dr. D. If you look at point E, we've got the same thing. You do, it's the same thing but different. It's same but different, okay? Because you have the angled ones coming off of there. So you cannot say that that's a zero force member from E to D if you're looking at the base, because the additional Y force has to be taken up. That's getting pushed through EF and EB, has to be taken up by ED, right? So it's non-zero. Okay. Well, we'll get into that more. And then we're told that this has a really annoying distance of being 2.33 feet, or 2 feet and 4 inches, right? But luckily for us, that means that this then becomes a 2.33, 8.33, or sorry, I did that backwards. 8. The standard 2.338, 8.33 triangle that everybody knows and loves, right? It's one of those ones that they definitely cover in geometry for sure. Or you can find the angle if you really wanted to. That's the point, right? But you need something there eventually. All right, so we're just doing reactions first. For the reactions, I'm going to do the hard one up front. Nailed it. Great. We'll make that 0 later. We're going to redraw all of our joints later. Some of the, I'm going to do the sum of the moment first. Sum of the moment, I'm going to use H. Again, doesn't matter where you do it. I just did H. So I'm going to start at 8 feet away, right? Because the 300, this first 300 goes through H. So we get negative 600 times 8. To remind ourselves, X and Y. Okay, down. Then you're going to have, is that negative? No, that should be positive. Positive, like I said, positive 600. Plus 600 times 16. Plus 600 times 24. Plus 300 times 32. Minus AY times 32. All stacked up and nice. Look, we can solve for AY immediately, right? And AY is equal to 1,200 pounds. Okay. We got 2 of our 3. And again, we said by symmetry, right? This has to, I think this makes sense if you look at it, right? If you look at it, this is symmetric, it's symmetrically loaded. So both of those forces have to be equal, right? But let's double check. 300 or 600 times 3, right? Let's just do it. We'll sum the forces in the y. Y is equal to 0 is equal to, I got 3 600s. These are negative. Minus 300 times 2, because there's 2 of them, plus AY plus HY. Okay, well, it turns out that 300 times 2 is 600, and 600 times 3 is 1,800, and when you add those up, that's 2,400. And if I move that over, I get 2,400 minus AY is equal to HY, and so HY is also 1,200 pounds. Great success, right? We got the reactions. Okay. Cool. Any questions so far? Reactions. Reactions are pretty straightforward for this one. Not too bad. Nothing crazy, no like applied moments or anything like that, or distributed loads. I originally tried to incorporate a distributed load on this, but that made the problem very, very mean. And I decided against that. You're welcome. Okay, so next thing. We are going to now start with our joint analysis, right? I'll save my reactions up here in case I want them. Okay, so here's what we need to do, right? What you're going to see me do, and I think is a best practice for doing method of joints, is to draw the joint while you are doing that part of the problem. Don't draw them all up front. And the reason for that is once you start to find tension and compression, you can help yourself a lot by drawing them in the appropriate sense once we find out if they're tension or compression. Okay? So I started with joint A. Do you have to start with joint A? No, you can start wherever you like. So why would I start with joint A? Because it's joint A. I only need to know 2 things. It looked simple enough, right? What do I got? Well, I've got this thing here. I'm going to assume everything is in tension to start. I'm going to call this FAB and this one FAC. This is joint A. And I know that I have a reaction here, AY, which is 1,200 pounds, right? And I know that I have a force pushing down at A with 300 pounds, right? I also know that that's a 3, 4, 5 triangle up here. So we will write it in 3, 4, 5. Okay. Remember, when we have pins, we get two equations. All right, that's it when we're doing method of joints. Two equations. So I'm going to use sum of the forces in the y direction is equal to 0. Why would I do the y first? It's actually going to let me solve for something, and then I don't have to write another equation and then come back to it, right? That's really it. It's not a big deal. You can do either one. Doesn't matter. All right, if I solve this first, what do I get? Well, there's only one x direction applied force, right? So I get minus 300 plus 400. Yeah. Or sorry, 1200. Why did I write 400? Jeez. That would have thrown everybody off. How am I supposed to know that? All right, plus 3/5 of FAB. So FAB, right off the bat, and I'll put it up here, is going to be, well, it's going to be negative 900 times 5/3, or negative 1,500 pounds. So 1,500 pounds compression. So we know that's in compression. Okay. We know that's in compression. And so now you have one of two options for the second equation. You can either carry the negative sign with it, or you can redraw it, which is the same as carrying the negative sign with it. It just changes how your equation looks. I'm not going to redraw it because I'm going to pretend that I'm doing this on paper. And in fact, if you were to look at my paper, I don't redraw it. I just carry the negative sign with it. Sum the forces in the x direction is equal to 0. Well, I got FAC plus 4/5 FAB, right? Okay. FAC is equal to negative 4/5 times negative 1,500. Because I did not flip the sense of my vector. Had I flipped it and redrawn it, you will see that this equation changes to FAC minus 4/5 FAB, right? But it takes care of itself. Turns out that FAC, when we crunch that, is 1,200 pounds. Yeah. 1,200 pounds in tension. And now it's just rinse and repeat, right? So we can go to joint C or we can go to joint B. I'm going to go to joint C. Why? Because it's easy. And we'll just do that next. Any questions so far? Okay, joint C. Here's joint C. Well, I've got what? I have FAC, which is equal and opposite. We know that it's in tension, right? So it has to be pointed this way. And then I've got FCG, which is FC towards G. Is that G? No, that's E. Never mind me. Don't worry about that guy. There it is. We also said that this was a zero force member, right? And I'm going to prove it right now. How am I going to prove it? Look at it. If I sum the forces in the y direction, there are no forces in the y direction. It has to be 0, right? Okay. Next thing, sum forces in the x direction. This one's very interesting. Okay, so we found out that this and this are equal. There you go. FCE and FAC are equal. Right? That's joint C. Cool. We got to do two more, and then we've got everything that we need. Dr. D says. But do we believe him? I don't know. I wouldn't believe him. Okay. Any questions on joint C before I erase this and go to joint B? Ooh, that's a big crack. Probably going to hear it on the video. All right, B is a little tricky, admittedly, not because of anything other than it's a pain with that extra other angle. Okay, so there's a couple of things here, right? First, we know that FAB is compression, right? So we're going to draw it in compression. And we know that this is a 3, 4, 5 triangle. We also know, well, we know that there's a zero force member that we're not going to bother drawing, right? We have an applied 600 pounds straight down here. We've got this force, which I'm going to call FBD. And this triangle we established has these weird dimensions, but still has them. And then the last one that we have is FBE, and that also is a 3, 4, 5. Okay. So what we know FAB, right? We know FAB. We know the 600. We're missing two of the forces. In this case, we are going to need both of the equations, and we're going to have to solve them simultaneously, right? This is the trickiest one in terms of that. So if I sum the forces x direction, set it equal to 0, I get 4/5 FAB, right? Because that's pointed in the positive x direction, plus 4/5 of FBE, plus 8 over 8.33, repeating, of course, FBD. And yes, it was a Leroy Jenkins reference, and if you don't get that, I'm old. So if I expected you to get all of my references, I'd be living in a much different world. We can't solve that yet. Two unknowns. We call it one. Sum the forces in the y direction. Well, okay, all of these get changed to their counterparts, right? The FBE is pointing down and to the right, so that's going to be a negative in the y direction. Plus 2.33 over 8.33 FBD minus 600. All right, so now we have to do a little bit of algebra, right? Which one? Where am I going to do my algebra? I'm going to do the y direction equation. Why? Because it has a 600 in it, and I can get some numbers pretty quick. It doesn't matter. No, it doesn't matter. Right, so if I take my y direction equation and rearrange it, I get 1,000. Right, where's the 1,000 come from? Well, remember FAB is 1,500. 3/5 of 1,500. So let's do it all out. Let's do it out for everybody. So I'm going to move the 600 over. 600 minus 3/5 of 1,500 is equal to 3/5 of FBE plus 2.33 over 8.33 FBD. Okay. Now you can do a fun thing, he says. where you multiply through by the 5/3 right now, right? And that's where you get the 1,000 from. So I'm going to go ahead and do that. If I multiply both sides by 5/3, right? Like this goes away and that goes away, but I have to multiply the other two. So 5/3 times 600, right? What's that? 5/3 times 600, that's our 1,000, right? 600 divided by 3 is 200 times 5 is 1,000. 1,000 minus 1,500 is equal to FBE plus 5/3 times 2.33 over 8.33 FBD. And that's gross, but there we are. Okay, so now I'll solve this for FBD. Okay, turns out that this number here, when you crunch it, is roughly 0.467, right? Which I mean, probably wouldn't even need a calculator for that. Fine. Okay, so if I solve this for FBD, I get 2.14 FBE minus 1,071.43. So it's very clean looking, nice, beautiful numbers. We'll call this 2.1, and we're going to plug that into equation 1 now. All right. But overall, this is really the only time that we have to do a simultaneous solving. Most of the other directions, we could get something right off the bat in either the X or the Y direction, right? It's not too bad. Okay, so we take that and we plug this into the X direction equation, right? So let's see. That's going to be negative 4/5 of 1,500. I'm moving the FAB component over. Is equal to 4/5 of FBE plus 4/5 of this gross expression down here. And we can solve this for FBE now, right? And we have to do a little bit of work to do that. Notice something really, I'm gonna say, it's not really cool, but something very useful here is that everything is divided by 4/5, right? So we can just go ahead and get rid of that now. I forgot to include my 8/8.33 here. That still exists. Don't forget to put that in there. But because everything has a 4/5 term, right? Well, I guess everything doesn't, does it? Never mind. Don't cancel the 4/5. I am off notes right now, and that's when I get into trouble. So like I said, you can't cancel anything. And these are all gross numbers still over here, right? We can punch them out, and we will get less gross numbers. So we'll get negative 1,200. We're going to go up here now. Negative 1,200 is equal to 4/5 FBE plus 2.05 FBE minus 1,028.57. And now we can solve for FBE. And it turns out that if we solve that whole thing, FBE is negative 60 pounds. It's negative 60.06-ish, but I'm just going to call it negative 60 pounds. And that is compression. So I'll go back over here. I'm going to erase the X direction equation to make room for FBE is equal to 60 pounds compression. Okay. Now I got to take that and I got to plug that back into equation 2.1. This guy right here, right? To find FBD. Because I didn't redraw it, I have to keep the negative sign with it. Right? And turns out that this ends up being negative 1,200 pounds, which is also compression. So FBD is negative 1,200 in compression, or 1,200 in compression. So I'll erase the Y equation and put it on there. We only need to solve one more, and that one's much easier. We're going to finish with joint D, because the only force left that we don't have before we go into symmetry is the force in member DE right down the middle, right? And remember, we can't call that one 0 because there's extra things that end up popping off it, but we're also going to prove it to you why we can't call it 0 in a second, right? So why wouldn't you use letter E? Well, you could if you wanted to. But I want you to also notice that if you use E, there's 4 different forces that you have to take, or 5 different forces you have to take into account, whereas this one has 3 plus an applied force. So it's less things. And less typically means we have less room for making errors. Unless you're me, and then you'll find a way. But don't be like me in that respect. Okay. Questions so far while we're moving through this? No? All right. Joint D. We have our 600 pounds pointing straight down here. And we've got FBD, which we found was compression. So we're going to draw this in compression. And we know that that's that weird triangle, right? The 8.33, 8, 2.33 triangle. We also have this force straight down that I'm going to call FDE. And then we've got this force, which I will assume is in tension, FDF, and it's the same triangle as the purple one. I'm not going to write it out again. All right, so looking at this, just looking at it, I am expecting that FBD and FDF are going to be the same, right? And the reason is because they are the only 2 forces that have x direction components. And so if I sum the forces in the x, they have to balance each other, right? But we'll double check. X is equal to 0 is FBD. Well, let me put the component in there. 8 over 8.33 FBD plus 8 over 8.33 FDF. There are no other x direction forces, right? In this case, these do cancel, right? Because I can multiply by 8.33 over 8 on both sides, and that gets rid of everything. Or divide through by that if that's how you like to think of it. So this tells me that FBD is equal to FDF, FDF equal to FBD. That's lovely. And the reason that's lovely is because now we know everything we need to know to set this up. Plus remember, I didn't redraw it. I'm going to carry the negative sign with me? So you can't, I know what you're doing. You're looking at that and you're like, that looks like I'm just going to cancel those out. But remember, there's a negative sign attached to that FDF. If you were to actually draw both sides in compression, this force is actually pointing that way. So it's additive, right? It's an additive effect. Okay. So let's keep going. 100. Oh, let me put the number in. Okay. These will be additive. And now when we solve this for FDE, we find that FDE is very strange, but it's 72.5 pounds in tension. And the rest of it is symmetric when we look at it. Meaning what? Meaning, well, let me show you. Maybe I'll show you. Move this over here. Get rid of these guys. Get rid of all of this. Just so that we can go back and look here. So what do we know? We found this guy and this guy. We know that's 0. We found this. We found this. We found this. And we found this, right? And we found this. We calculated all of these. If we look at the rest of them, based on symmetry, we can say, well, FEF and FBE are the same. This is 0, right? Because that one was 0. Okay. So we found that now. We got this guy. FEG. Well, that should be the same as FCE. FGH should be the same as FAC, which is the same as FCE. And then FH is FAB. Duns, Dunzo, Dunsky, Dunaruski, all those things. Sorry. I was just trying to do this. I ruined it for everybody. There it is. Okay. How do we check it? Well, pick a joint and check it. One that you haven't solved yet. I picked H. I'll show you how to do that. If I look at joint H, nope. I want to look at joint H first. Stop it. Click on the thing. Why am I going to pick H? Well, why not? It doesn't really matter which one I pick. Unless I keep doing this, which is a fun game, admittedly. So this is 1,200 pounds upward. We have 300 pounds downward. So why would I pick this one instead? FGH. I'm going to write that in as, where is it? FGH is 1,200 pounds. And then this we found to be in compression. That's FFH. FFH is 1,500 pounds. Okay, I'm going to sum up all my forces in each of the directions and make sure that they make a 0. Right? All right, so let's sum the forces in the x direction. And if I do that, that is, well, in the x direction, I've got negative 1,200 plus 4/5 of 1500. Okay. Check. Nailed it. Sum of force in the y direction. 1200 minus 300 minus 3/5 of 1500. Okay. There. Static equilibrium has been maintained, meaning that the results of those are correct.
I have a question.
Yeah. Mm-hmm.
You had eight, like an 8x component.
Mm-hmm.
I thought that was a rocker, so I thought it was.
So let's see. No, this one's a roller over here, and this one's just a pin. Yeah. It doesn't affect the overall method of joints, right? Because it's 0 in the x direction anyway. But yeah, rocker will have, it'll be a very pronounced curved bottom. All right. Any other questions? Okay. All right. So check it out. This is a stadium truss. It's called that because they use them in stadiums. I know. Find the forces AB, AG, and FG. Don't forget to tell if they are in tension or compression. This is a method of sections problem, 100%. And the fact is, you should be very much looking at cutting this right here, kind of like this, or whatever angle you want, but it needs to cut through these three members because you need to find these forces, right? But let's go back. Let's do our normal progression. So the normal progression says, what are our knowns? Dimensions and our applied forces, right? Find FGA, FBA, and FGF. I wrote those very specifically in that direction because you 100% do not need to find the reactions to do this problem. Why don't you? Because all the reactions are to the left of the point where I'm cutting. So if you wanted to, you could find the reactions here, and that's fine. But if you didn't want to find the reactions at all, you could just cut it and use the right-hand side of this FBD. Whatever you want to do. Both of them will come out correct. If you're going to do the left-hand side and use the reactions, then you point this one along EK, and this one becomes an X and a Y, right? But it's fine. Let's draw our FBD. So if I draw our FBD, there's a couple of things we need to point out here. B, G, C, D, H. There, perfect. C, E. Man, this is not a great drawing, but okay. We're gonna roll with it because reasons. I'm gonna call this angle phi in here. Why? Reasons. It's better than not calling it anything. Okay, when I made my cuts, I've got three forces here, right? I've got F, G, F. I've got F, G, A, and I've got F, B, A. This points at point A, and this one points at point F, and this one points also at point A, right? Why did I do that? For reasons that you will see in a moment. But I got to put some dimensions here. This is 9 feet. This from F to G is 12 feet. And then the other two, even though they're not drawn this way, are both 14 feet. Okay. Here's the problem. I'm going to call this distance right here y, from B to G. And the problem is that I don't know what that distance is. Now, do I need that distance? Probably at some point I'm going to need that distance, right? Depending on how I do this problem, I might need that distance. Do I want to worry about what that distance is? No, I don't, right? But first thing I'm going to do is let's look at this, right? What if I had a triangle that looked like this, where this was like 9 feet high and it was like 40 feet wide? What would that give me, right? Well, I'd be able to find phi, right? Phi being the angle, and I could say that the tan inverse of 9 over 40 is something, right? So phi should give me like 12.68 degrees, right? And we're going to need that angle for sure, right? But if I wanted to find that distance y, how would I do that? Well, now you have the angle, right? So it becomes pretty easy. Or you could use similar triangles too, right? Because we know that this distance from here to here is 28 feet, right? From D to G. So if you used similar triangles, you would know that, let's do it this way, y divided by 9 is equal to 28 divided by 40. And so if I solve that for y, I get 6.3 feet, which is great. Right? Okay. So let's get into the solving of this. First thing I'm going to do is I'm going to sum the moment at A. If I sum the moment at A, I can solve for FGF right away. Sum the moment at A equals 0, right? Gives me negative FGF times 9 minus 1.8 times 12. I didn't put my forces on here, did I? And it's in kip. Gross. Minus 0.9 times 40. Minus 1.8 times 26. Sorry, I did that out of order. I apologize. We can solve directly, right? And we find that FGF is equal to negative 11.6 kip, which is compression. Okay. Next thing that I'm going to do, in the spirit of eliminating more forces, I'm going to sum the moment at G. If I sum the moment at G, I can solve for FBA. The only difference here is that FBA needs to be broken into components, right? The Y component of FBA is 0 because it passes through G. So I just need the X component. So I have FBA times the cosine of phi times 6.3, which is why I needed that angle, right? Or why I needed that distance. Minus 1.8 times 14 minus 0.9 times 28. So FBA ends up being 8.2 kip tension. And then get one more equation. You can do, I guess you could, if you wanted to continue with the moment trend, right, you could sum the moments at H. I'm certainly not going to do that, but you could, right? Because FGF and FBA both go through H, which leaves you with FGA right? I'm just going to sum the forces in the x direction for the last one. Sum forces x is 0 is equal to negative FGF minus 4/5 FGA minus FBA cosine of 12.68 degrees. Right, and we can solve directly for FGA. Remember that you have to carry the negative sign in here because we didn't redraw our FBD. Right, so we end up with FGA is equal to 5/4 11.6 minus 8.2 cosine of 12.68 FGA is equal to 4.5 kip tension. You can check it if you want, if you use some of the forces in the y direction or another moment, you can double check and see if all the things check. Was not asked to do that, but it was available. Okay. Right? Questions? One's pretty straightforward. Allows you to skip having to do reactions altogether, right? If we do it in that way. If not, if you did it the other way and you found the reactions, I'll check that too. That's fine. Just because I did it one way doesn't mean it's wrong. If you did it your way, I'll give it a full once over, probably a thrice over. Anything? Questions, comments, anything on this one? Nothing. Okay. The last one. This one is find the reactions at C and the force in member BD. It's pretty straightforward. So we need to find the reactions here and the force in this member. 3 forces, X, Y, and FBD. First question that was asked, though, was what is the difference between a frame and a machine? Okay, a frame has no moving parts. A machine has moving parts. That is the definition as provided by Sir, forgetting his first name. Let's check real quick. And I knighted him also. Sir R.C. Hibbler. Stands for Reginald Charles Hibbler, which I just made up. Okay. Next question. What is the difference between a truss and a frame? A truss is only comprised of 2 force members. A frame has at least 1 multi-force member. That is the difference. Okay. All right. What do we know? Let's get into it. Known. F equals 400 pounds and distances. Find. We were very explicitly told to find the reactions at C and the force in member BD. Very explicitly. Free body diagram. Here's point A. Here's point B. Well, that's not point B. Never mind. Here's point B. And here's point C. CY. CX. FBD. Distances. I'll put point D up here just for references. Oh, forgot one. Sorry. Bless you also. 400 Newton. All of these distances are given in millimeters. I'm going to write them in meters. There we go. That's our free body diagram. 3 forces, 3 equations, 3 unknowns. Okay. Okay, first thing I'm going to do, knowing nothing else here, I'm summing the moments at C. If I sum the moment at C, that's fantastic. I need to do what then? Well, which forces do I have? Well, I have that 400. That 400 pushes downward, so that's going to be a positive 400 Newton. How far away is that from point C? Well, it's 0.45, it's 0.135, right? 0.135. I also have the component from FBD, and the way that I have drawn FBD, this is going to be pushing to the right in my drawing, right? Which would also be a positive moment. So what's my component though? Well, I need the x component of this, right? Because the y component passes through point C. So if I want the x component, that's 0.24 over the hypotenuse of that, which is 0.51, which actually, if we go back and look, is given this distance from here to here. You don't even have to do any trig for it. It just tells you how long that is. Okay, and that's times FBD. And what's the distance that is away? Well, that's 0.45 away from there, 0.45 meters. Oh, well, looks like I drew FBD in the wrong direction. Wah, wah. It's really going this way. Which, granted, probably makes more sense, right? But here we are. That's fine. So it doesn't matter. We'll figure it out later. Okay, now that I've got that, that's really super fantastic. What should I do now? Well, I need to go after one of my CX components, right? So I can sum the forces in the X and the Y, and that's fine. I could do that. Or I could be super fancy and keep using my moment equations, which is what I'm going to do. And I'm going to get CX directly. Turns out, in this case, we get negative CX times 0.45 as it pushes in the clockwise direction. 400 is still positive. Solve for CX. And I should hope that it is positive, and goes to the right because FBD is pointing the other way. And since there's no other x direction force, they have to be equal and opposite, right? And we can check that because, 0.24, turns out that 0.24 over 0.51 times 255 is 120, turns out. Very easy math, very easy. It's not, it's just why you have a calculator. Anyway, last one. I got everything else I need. I'm going to sum the forces in the y direction. You could get creative and do the moment at D, I guess, if you really wanted to, right? But you can't because that, I mean, you could. I wouldn't. Do whatever you want. All right, I'm just going to do it this way. CY plus 0.45 over 0.51 times FBD minus 400. Don't forget that 400. That will ruin your entire calculation if you forget that 400. Remember, because we didn't redraw the FBD, the negative sign carries into this equation, right? And so we end up with this really, I would remind you that this is negative 255, right? So when we go to solve this, it's like we're actually adding these two numbers together. And this is going to give us 0.45 0.5 over 0.51 times 255 plus 400, which is 625 newtons, and it's pointing upward. Great success. You can check it with the x direction equation if you want to. It's up to you. It works though. Great success. If I were going to vote on one of these projects or these prizes, I would pick ice cream sandwiches, 100%. That is what I would choose. But there you go. You guys can pick whatever you like. I'm sure the purple hair will probably be close to the top. Okay. I will get these graded as quickly as possible. Asher, what's up? Because it's pointed specifically along the bar. Now, if you choose, there is a reaction at D, but if you go to solve a reaction at D, that creates 4 equations or 4 unknowns with 3 equations. So it makes it impossible to solve, right? And so you have to break it into its component. The other reason is we know that based on how that looks at, well, the way that I've drawn this free body diagram, and I'll erase this for a second just to go back. I eliminated this bar, right? I only drew it for the L-shaped portion. And so I understand that if we wanted to, right, we could go back and look at the other side and solve for dy and dx. It's just an extra step, right? We have the angle, we know the distances, it's just breaking it into components, right? And they should be basically the same thing as there. Okay. It's just extra steps. Okay. Next, yeah, any other questions? Any other questions? No? Nothing. All right. Okay. Well, then we're gonna go back. Nothing, pulleys, recognizing zero force members. Pulleys. Pulleys seem the big thing here. Yep. Yes, indeed. Okay. Thing to remember about pulleys is, when you draw the free body diagram, if we are assuming a massless and a frictionless pulley, more importantly, frictionless. If we're assuming a frictionless pulley, then the force transmits completely on one side and the other, and they have to be equal, right? If there's friction in the pulley, then they don't have to be equal, and that complicates things, and that's why we, so I'm going to give you an example of when there's friction in a pulley. You guys, when you're on an escalator, if you grab it and you pull the rubber part as hard as you can, you've now created friction in there, and it creates slip, right? And the slip is a problem. And it also makes people ahead of you on the escalator really uncomfortable because their arms get jerked back like that. So please don't do that. But that's what happens when you have slip or friction in a pulley. It doesn't transmit the force evenly, and you get those jerky sorts of motions, right? When you're looking at pulleys specifically, draw the free body diagram of the pulley, right? I know there was a homework problem where you didn't have a massless pulley. They told you what the pulley weighed, right? If you're doing a statics problem and you know the weight, that's just another force that you draw on there, right? It acts from the center of the pulley straight down, and so you need something to counteract that to hold it up, right? It's the whole thing. Do you see pulleys super often? That depends on what you do, right? I would say that as a mechanical engineer, your likelihood of running into pulleys is probably pretty high. As an electrical engineer, it's probably pretty low. Biomedical engineers, I mean, I can probably make an equivalent statement about pulleys and how certain tendons in your body work, right? Specifically about your knee or your wrist, right? So There's all those things. Okay. Computer engineers, probably not so much, unless you got some really cool cooling system that I don't really know about that uses pulley, which I'd be interested to see. Um, okay. Distributed recognizing zero force members is tricky for sure, right? It's tricky. And if this weren't a 7-week class in statics, you'd probably feel a little bit more comfortable because we'd have a little bit more time to get used to the idea of when we see zero force members. But it's really it's a matching game, right? If you think about it, right? We understand that there's certain conditions through which these things have to be zero force members, right? And it's just looking for those very specific conditions. And if there's anything off from those conditions, the answer is it is not a zero force member, right? For instance, the one in the quiz we just went over, it looks like a zero force member, right? It looks like, hey, we've got this loading, right? At point E, we had that loading, right? Where we had these sorts of forces. And your gut feeling is, hey, well, okay, in the X direction, that all needs to carry, and so that Y direction is 0, right? But because these are at an angle here and here, right? Because, yeah, come on. No? Okay, never mind. We won't use that thing. Because those are at an angle, those also carry a Y direction force, right? They carry some component in the Y direction. And so that member in the center cannot be 0. Now, that is similar, but not the same as this condition, where we have a T, right? So I want you to think about that as if you had a pipe, right? If you had a pipe and you had if you had water moving really fast in that pipe, right? Or just water moving in that pipe, it's along the ground. It's not going to go up unless there's something forcing it up. It's going to travel straight through, right? If I put some kind of pump at that joint, now we're pushing water upwards, okay? If I have it at an angle, it's going to come back up, right? It'll come back up. But zero force members is all about practice. And I will be honest with you, when I was going through statics as an undergrad, I tend to use the hammer a lot. I tend to brute force a lot of these problems when I was first doing it. It's the same thing when you go through coding, right? I bet you if you go back and look at some of your early code that you've ever written, you'd be like, man, I really am not embarrassed at this at all, right? You would be told, your future self is very embarrassed by your younger self all the time. That happens, okay? Learning is not pretty all the time, guys. All right, let's talk about what we did last time. It's been a while, almost a whole week, right? But last time we talked about internal forces specifically, right? And so how do we find internal forces, right? Well, we understand that if we were to cut some member that was under a load, right? Typically beams is where we're going to use this the most, then we should have some internal force that is joining our beam together, right? So we take an imaginary cut where we are interested in finding those internal forces, right? Then you choose one side to work with, right? Which one do you want? That's totally dependent on your preference. If necessary, determine any support reactions. I disagree with this. We talked about this last time. For beam problems, you will see me today. I always start with the reactions, especially if we are going to be drawing shear and bending moment diagrams. You need those reactions. You need those reactions. We'll go over a couple of different ways to do shear and bending moment diagrams, right? Draw the FBD of your structure. Show N, V, and M, so your normal or your axial force, your shear, and your bending moment, and then apply your equilibrium equations, right? So you have typically 3 equilibrium, well, not typically, you have 3. It's a 2D problem. We're not, I tell you right now, we're not going to do any 3D beam loadings. As much fun as that sounds, we will not be doing that. Okay. So in a multi-force member, the member is generally subjected to an internal, normal, shear, bending, or all of the above. Yeah. All right. We we got lots and lots and lots. Nice. Yeah. Short stack, I'm gonna need you. I'm gonna need you to commit on this one. No questions. I'm asking the questions. Commit to an answer. It is. It's D. It's all of the above. Good job. Good job. All right. So yeah, it has all the things. One more here. The component V acting tangent to or along the face of the section is called axial shear, normal, or bending moment. All right. And it's B, shear force. Great. All right. So let's look at this problem. Okay. This one looks pretty fun to do for sure. All right. So determine the normal shear and bending moment at point C in this beam. Okay. Great. So there's a brute force way. Okay. There's a brute force way. And there is let's call it an elegant way, right? A clever way to do this. Okay. And they'll both work, right? So what's the brute force way? Well, all right. So if I was going to cut this, I have two options, right? Two options. If I cut this at C, I can either use the left side or I can use the right side. Now, based on the principles of static analysis, they should be equal, right? So if I do it one side, I should be able to check with the other. That is true. You should be able to check with the other. All right. But which side? Let me ask you this. If I was to ask you to do this problem, which side would you use? The left half FBD or the right half FBD? All right. Why the right? That's true. You don't have to worry about any of the reaction forces. And you get the added bonus of, well, I was going to do it both ways, but just to show you. But you get the added bonus of this, which I'm going to show you right now. If I cut it here, is this a triangle? So you got to figure out how to break this into a rectangle and a triangle, and you got to figure out how much of this, like how big is that at this point, so you know what. It's a pain, right? It's not impossible, but it's a pain. But that's the brute force method, right? So we would have to figure out the reactions, and then we'd have to deal with this compound distributed load, right? Which is doable, right? We know how to handle that, but let's not. Let's do it the clever way, the elegant method, if you will, as some would say. It's not gonna work. I gotta use this guy. All right, so let's get our thing. That looks good. We know that if we split this, it is exactly 1.5 meters when we make our cut at point C here. At point C, if I cut it there, I'm going to have shear, V. I'm going to have some bending moment going that way. And a normal force. Great. The only force that is acting on here is this distributed load, which is triangular, right? And we were told what? That is 1200 Newton per meter, right? The problem is that that's not exactly true. We were told that that was 1200 Newton per meter at the far left, right? At the far left. It's not 1200 Newton per meter at C. So we need to figure that out. So, all right, so how do we do that? How would you characterize this portion of the triangle from here down to here? If I asked you, I don't know, to write an equation to take me from this point up to this point, what would that look like? Yeah, it's a linear function, right? It's a line. So given that we split it at 1.5, right, which is halfway through, we can say, since it's linear and it goes from 1200 to 0, we should be at the midpoint of that function, right? Should be 600 Newton per meter. Can we prove it? Okay, well, sure. It goes from 1200 to 0, so our m, our rise over run, should be, what, negative 1200, right? So it goes downward. The run is, what, 3? So the equation should equal, right? And the y-intercept should be 0 since it hit 0. Negative 400 times 1.5 gives us negative 600. But since we're moving up, right, we don't really, the direction of the slope doesn't really matter here. It's the magnitude that we're worried about. So that's where the 600 comes from. Does that make sense? Make sense to everybody? Equation of the line, always, it's coming for you, no matter what you're doing. Just ask Ohm. All right, so we got our 600. This looks pretty good though, right? Because now we know that we've got some force here, right? And that's going to be 600, 1/2 600 times 1.5, so the area under the curve. Turns out that that's 450 Newton. And I know that says brute force method at the top. This is not the brute force method. This is the elegant method. Where does this occur? Where does that occur? 1/3 from the fat end. Okay? And that's great because we can start off here, right? So what do we find out? Hold up. I sum the force in the x direction is equal to 0 is equal to my normal force. That's the only explanation, right? I have no normal. I'm not loading this in the x direction. Great. Sum the forces of the y. V minus 450. Shear is equal to 450 Newton. Great. If I sum the moment at point C, it's a negative moment that I have drawn there. The only force that I have is that 450 times 0.5, which is also negative from point C. So the moment is negative 225 Newton meters, which means it's actually going in the counterclockwise direction, which means it's actually a positive moment, right? But that's fine. And there we have it, right? Found it. Now, if you wanted to do it the other way, good, sweet, sweet baby Ray. Yeah. Sure. So for a triangle, we know based off of the table in the back of the book that the centroid in the x direction is 1/3 from the fat end of the triangle. Okay. Triangles and rectangles are the most common distributed loads that we're going to use, and so those are pretty you'll pretty much remember them. If you need something really crazy, like last class we had the parabolic one, then you gotta look it up. But I pulled out my moment of inertia chart here. So yeah, you can see the same thing right here. On the quiz, and there's a page for that, right, that shows you different shapes. But that's typically it. And next week or end of this week, we'll go over how to find mass moment of inertia and all that stuff. Super fun. Double integrals and all that. Everybody's favorite. I really don't want to do this with the brute force method, but I feel like I have to, so I'm going to. All right, so that was fun. And he said, and everybody said, not really, but okay. All right, so I'm going to keep these results up top so we can see them. And hopefully, if I've done this correctly, right, I should get the same results again, right? Understanding that n is 0. And I think I can prove n to be 0 pretty convincingly in a second. I'm also going to keep that equation right here because it's the same thing. We're good here. This line, no matter how long it is, has the same slope, right? Everybody would agree with that. Maybe you don't, and that's fine too. But you would be wrong. And if you like to be right, then you would agree with that. Okay. So this is what we want to do. First thing I'm going to do is I'm just going to use the same free body diagram because I have that luxury. And I'm going to draw the opposite forces, right? So now point C is over here. In this case, I've got shear, I've got bending moment, and I've got an axial force. But if I look at my reactions, unfortunately, draw them this way, I've got AX, I've got AY, and I've got the moment about A. Why? This is why this is where this gets tricky, right? I also, before I do that, I've also got this. I have this portion of this, right? And this is 1200 Newton per meter. And we just found out that this is 600 over here, right? Newton per meter. Yeah? Based on the equation of the line that we found. Okay. So we need those reactions. First of all, I'm going to go back here. If you look at this, I clear this off. This is bolted to the wall. So it is a fixed connection that has AX, AY, and MA, right? It's going to prevent bending. It's going to prevent any motion from that point. We do not want this to bend. And at that point, you're like, well, Dr. D, if you didn't want this to bend, you probably shouldn't have built it as a cantilever. Fair point, right? Why would you do that? Great. So how do we do this, right? Well, we need a free body diagram for the entire system. So this is our, all right, so let me go ahead and do it this way. To get our reactions, okay? Here's my reactions. I know the entirety of the beam is 3 meters, and I know that I have some distributed loading, which I'm just going to draw as a point force that is 1200 times 1.5. So 1200 times 1.5, what's that? Something 1800. And this is 1 meter away. Yeah. I did. It doesn't really matter, but I will adjust this one. I'd rather have it be positive when I make my assessment. All right, so if we're solving reactions, AX is 0. Does everybody see that AX is 0? I hope so. Similarly, some of the forces in the Y, AY is 1800 newtons. It has to be. It has to balance. It's the only force on there. It has to balance the rest of that distributed loading, right? It has to. It has to balance all of it. All right, sum of the moment. I sum the moment at A. What does this give me? Well, we know that that's 1 meter away. I have MA, which I assume to be positive, right? Minus 1800 times 1. 1800 Newton meters. Okay, we quickly find the reactions and we'll substitute them in here. I'm not going to draw that, but that's why now you can see it, right? There's no x direction forces on this, so we're expecting that the normal is going to be 0, right? There's no axial loading here. We don't have to deal with it. All right. Get rid of this for a second. (1800 Newton meters). If I'm looking at this, I have 2 distributed loadings. Okay, I have a rectangle. The rectangle is 600 Newton per meter and 1.5 meters long. What's my area under that curve? Well, we're going to call this guy F1, which is 600 times 1.5, 900. And we've got this guy that I'm going to call F2. And F2 is, well, this is where it gets tricky. It's 1200 minus, it's 600 tall. 1/2 times 600 times 1.5, 300 times 1.5, 450, right? 450 Newton. And that's all well and good. And you know what? A lot of you are like, man, I really am looking forward to creating one resultant force at some distance away. And I don't know why you would want to do that, because we're not going to. Because I don't need to. I know the distance for both of these already, right? So it's 0.5 meters. 0.5 meters. And this guy has to be, from this end, 0.75 meters. So when I go to calculate the moment, I have everything that I need. I don't need to do the thing where I find x bar and all those things. I don't have to do that. Sum forces in the y direction is equal to 0. I've got negative 450 minus 900 plus AY, which was 1800. I think that's all of them, right? Minus V. Well, hey, look at that. That's 450. Well, hold on. It's 1350 plus 1800. Oh, man. Crazy. It matched. We sum the moment at C. We end up with MA. And the rest of these, AY is going to be positive, negative, right? Minus AY times 1.5. The rest of them are positive. Plus 450 times 1 meter. Plus 900 times 0.75. AY, we already know, is 1800. This also 1800, right? So, sorry, and I forgot to put the other one, plus MC. I almost forgot that because we're solving for MC. Foolish of me. All right, so that's what? That's going to be, if you put everything in there, right? 1800, it's negative 2700. No, that's not correct. Negative 225. Okay, so right. There it is. Great success. Is it any more difficult? A little, right? I wouldn't say it's earth-shatteringly difficult. It just is going to take you longer. You need to find the reactions. You need to deal with breaking this distributed load into two components, right? And then you do the math. As compared to what we did previously, which was I cut it once, I draw the free body diagram, and I'm off to the races, right? There's much less to do. Okay. Questions on internal forces there? No. Nothing. All right. Because we are going to get into, hold up. All right. Here's the things that are due. This is everything that is due until the end of time, or really until the end of the semester. Time should continue at the end of the semester, I hope. Dr. D-ism for the day, learning is a struggle. I think this one's pretty self-explanatory. If you're not struggling with concepts, are you really learning? Some people say learning is pain. I don't think that pain is really correct, but if you're not grappling with things, if you know everything already, then you are wasting your money on this right now. Okay. Types of loading and supports. Let's get into some real beam stuff then. Okay, these are beams. That's great. There's different ways that beams are typically held together, right? A beam is a structural member designed to support loads applied at various points along its length. I think that's pretty self-evident, right? And you can have concentrated or distributed loads as shown in this figure here, right? What we need to do in typically, so it's not like great, right? Everyone's like, great, I can cut a beam, I can find the internal forces. Why? Why would I ever want to do that? Why is that useful, right? And if you weren't asking that, maybe you are now. The real goal here is to be able to map what that internal force and bending looks like for the entirety of the beam, okay? I want to be able to look at a drawing or a picture and understand that no matter where I am along that beam, I can figure out what the shear looks like and what the bending moment looks like. Why? Well, from a structural standpoint, if I can tell where our maximum moment is and our maximum shear is, I can make design decisions based on those points, right? I can understand where I think things are going to break, and I can make a plan to hopefully have them not break, right? For beams, we typically have these sorts of setups, okay? On the top ones, we have our statically determinate beams, meaning that we can solve them with our standard statics methods, right? It's 3 equations, 3 unknowns. And on the bottom row, we have statically indeterminate beams because we have more unknowns than we have usable equations. And so we'll have to find equations. We really need to focus for this class on the top half, right? And so we have a simply supported beam, which will have a pin and a roller, or a pin and a rocker, right? 3 unknowns there. We have an overhanging beam, which is kind of like a simply supported beam, except that the rocker is moved closer to the pin, right? Think of a diving board. That's a simply, or that's an overhanging beam, right? An overhanging beam. And then if you have a really bouncy diving board, that's more of a cantilever beam. Okay. Cantilever is that it's held on one side and that's it, right? And so that fixed support has to take into account all 3 of our reactions. Again, in practice, you might see something like this continuous beam, right? Because what's the issue? I know that we neglect the weight of the beam when we're doing our calculations, right? But in practice, if a beam is really big, it's going to be really heavy. And if I have the beam and I'm only holding it at the 2 ends, what's going to happen in the middle of that beam? It's going to sag, right? And then it's not beaming anymore, all right? Which is a technical term, okay? And so what do? Well, we're going to have to put continuous supports along the beam to make sure that we don't get too much sagging or bending in the beam, right? It doesn't mean, again, this doesn't mean we can't solve it. It just means we have to be more creative in the way that we do solve it, okay? Okay, great. So shear and bending moment in a beam. It's probably pretty similar to shear and bending moment in other things that are not beams. And that is true. It is. Okay. So notice that we did not say axial or normal and shear and bending moment. We're specifically drawing the shear and the bending moment. Why? Because most of the time when we are looking at beams, we are not going to load them from the side, right? Most of the time. Are there times when that happens? Sure, but it's not typically the design. So what happens is we want to determine the bending moment and the shearing force at any point, right? At any point. So say again, it's point C, we would make a cut, right? We would see our 2 free body diagrams. We would probably all agree that this is the half that we would work with, and we would find the shear and the bending moment, right? And that's great, and we can do that, and we've seen how to do that. And it's the same process, right? But let's say that I want to map it throughout the entire beam, okay? So I make a bunch of cuts, and then I will say, okay, well, first I find my reactions, right? Because we need to know that to understand how much shear or bending moment we have going on. And then I cut it at some distance x, right? I'm just going to cut it right here. We call it point C. It's some distance x away, right? And if I do that, I can say, well, at x, I cut the beam at C, and I have, my shear has to balance my reaction, right? My shear has to balance my reaction, and my bending moment is a function of how big of a piece I cut off. In this case, it's the force times that distance, x. That looks like the equation of a line. Weird. Okay. What if I use this side, right, where I know the total length of the beam, right? So I keep moving along. Well, hey, in this case, I use this side. It's the same idea, right? And we can draw that over this period, right? I can say, okay, well, I have a shear of P over 2. And then at some point, I now have a shear that's negative. Where does that punch down? We'll talk about that in a second. Notice what the moment looks like. It increases linearly, and then it decreases linearly. Okay? Plus px over 2. L minus x. Right, so as this gets smaller, this is going to get negative. Okay? Let's go for it and see what happens. There's an important note on the last slide that I actually didn't go over. So it says right here, for a beam subjected to concentrated loads, shear is constant between loading points and the moment varies linearly. That's important to remember. Okay? This is a really important thing right here. I'm going to circle it, and then we're going to, maybe I'll circle it. I don't know. Right here, that guy, this guy, over here, this thing right here. Very important, very important. Look at what's going on here, right? And we'll talk more about it, right? But I found that the shear was P over 2. This stays constant until I apply a load, right? And then it drops. Why? Because there's a load pushing down on it. It changes the shear. I've now changed the shear from this point onward. It stays constant until I apply another load. Then it comes back up. Okay. Moment linear. So let's just go ahead and do this. So here's a simple, or that's an overhanging beam, right? I got this overhanging beam. I have the dimensions. I have these two simple forces on there. Great. First thing I'm going to do is I'm going to find the reactions. So in order to find the reactions, I will draw the free body diagram for said beam. I've got one force here that is 20 kilonewtons. I got one force here that's 40 kilonewtons. I have a pin at B. That's going to give me By and Bx. And I have a roller at D, which is going to give me dy, and I've got my distances, which tell me that this is 2.5 meters, this is 3 meters, and this is 2 meters. Now that I have my FBD, I will move the slide, but we have it still. Okay, well, we'll start how we always start. We'll do our static analysis. Bx is 0. Right? I'm going to sum the moment at D next. Why? I don't know. Because it doesn't matter. I just want to sum the moment and get one of the other forces. I could do it at B. I could do it at the 20 kilonewtons. I could do it at the 40 kilonewtons. Okay. So 40 kilonewtons, that's going to create a positive moment at 2 meters away. By is 5 meters away, and that's going to be a negative. And 20 kilonewtons is 7.5 away, and that's a positive. Solving this for By leads to 46 kilonewtons. Interesting. That's a lot of kilonewtons. Next up, we'll sum the forces in the y direction. Negative 20 plus By, which we found is 46, minus 40 plus dy. Turns out that dy is 14. kilonewton, which makes sense because we had 60 kilonewtons pointing down, so I need 60 kilonewtons pointing up, and 46 plus 14 is 60, and so everything is balanced, right? Ooh. Okay. So I'm going to use this opportunity to draw my real free body diagram. And by real, I mean I'm just going to put the forces that are actually on here. So this is 46 kilonewton, and this is 14 kilonewton. And then we need to start making some cuts. All right, so this is the first time that we are doing this, so we're going to slow roll and go through this, right? So we're going to start off by doing the cutting method, and then Wednesday we'll talk about a different method for doing this same thing that you can employ if you want to. Okay, so what's the idea here? All right, the idea here is we're going to make a bunch of cuts, and we're going to do the same analysis that we've been doing to find internal forces at all of those points. Okay, so where should I cut? All right, and so the first thing I'm going to do is I'm going to cut here. And I know that that looks like it's a significant cut, but we are going to cut an infinitesimal distance away from 20 kilonewtons. Okay, so when I draw it, it's going to look like it's huge distance, but it's basically going to be zero. I'm super zooming in when I draw it. Okay, we'll call that one very cleverly cut number 1. All right, the next one, there's different schools of thought on this. Okay, I could cut before the 46 and then after the 46. Okay, to show you the difference of what happens before and after. I would hope that you guys would see that if I cut right before 46, the only difference of me cutting right after 46 is that one of them is going to be 46 bigger. Right? So we're just going to cut here. Right? So essentially, where do I cut? I cut right after infinitesimally after each of my applied forces. Now, the last one, you have a choice, right? We're going to cut in the same spot, right, that I've, right, so like right after. So really that's on the 2. I know it doesn't look like it, but remember, it is a very small distance away from the force, okay? In this case, we'll talk about it when we get there, right? So we've got 3 cuts, right? We're going to determine the shear, and this is enough for us to shear and bending throughout the entire beam, right? Let's start with cut number 1. I'm going to draw a free body diagram for cut number 1. I'm going to draw it large, even though it isn't large, right? Why? So I can see it. The whole point of me drawing this is for me to have a tool to help in my analysis, right? It's the whole point. I got a shear, I'm going to call it V1, and I got a bending moment that I'm going to call moment 1. And hopefully you guys already see, right, this distance here is so small, I'm going to call it 0. Well, if it's 0, Dr. G, I explained it multiple times. It's infinitesimally small. If you really need to, you can call it 0.00000000001, or any number really, because at that point it's basically 0. Doesn't matter. It's the same. It's the same as a width of human hair. That's use that number. Okay. I sum the forces in the y direction equal to 0. Negative 20 plus V1. V1 equals 20 kilonewtons. Okay? Great. So what did we show? We show that the shear at the start of the beam is 20 kilonewtons. Okay, great. Now what? Well, now, oh, sorry, this would be negative and negative. Don't worry about my sign errors. Be worried about your sign errors. Okay, so it's negative 20 kilonewtons at the start of the beam, right? So we have shear there. What about the moment? Moment 0. The distance is 0, right? If I take the moment at the cut and the distance is infinitesimally small, the moment is going to be 20 kilonewtons times some really small number, which is also a small number. So I'm just going to call it 0, and we're going to move on. Perfect. Done and done. We'll save that. Save that result for later because we're going to need it. We're going to move to cut 2 now. So it's rinse and repeat, right? We take section 2. Okay. Here's section 2. I like to draw these so that it kind of shows the progression from one to the next, right? You guys can feel free to do it however you want. This is going to be roughly 2.5 meters. I've got my 20 kilonewton force over here. And I've got my 46 kilonewton force here. I got my moment that I'm going to call moment 2. And I've got my shear that I'm going to call V2. No normal because we don't have any axial forces. Rinse and repeat, right? Sum of the forces in y is equal to 0, is equal to negative 20 plus 46 minus V2. V2 is equal to negative 26. No, positive 26. It's equal to something. It's equal to 26 kilonewtons, right? So 46 minus 20 is 26. Move the V2 over to the other side. So we've increased our shear, right? It went up 20 from negative to positive. It switched signs on us. Directional change. Sum of the moment at point 2. Well, 46 kilonewtons is happening at point 2, right? Remember, we cut here. I'll show it on here. That's 2. That's 1. So really, we just have to worry about the 20 kilonewtons for our moment. 20 kilonewtons is going to give us a positive moment. It's 20 times 2.5 feet away. Plus M2. So M2 gives us negative 50 kilonewton meters. Right? And we'll keep these off to the side. Keep these off to the side until we need them. So far, so good. It's just rinse and repeat of everything that we've done, right? Guess what? We're going to do it one more time. This one, you get a choice. I think I know what choice you guys are going to choose, but I'm going to do it. I'll probably do it the long way instead. Maybe we'll do it. We'll do it both ways just to prove a point. Cut 3. This whole length is now 5.5 meters. I got 20 kilonewtons there. I got 46 kilonewton here. You know this distance from here to here, 3 meters. And then we got 40 kilonewton pushing down here. Now, why would I choose the left FBD instead of the right? Doesn't matter. Doesn't, yeah, because I'm just crazy like that. I enjoy doing these calculations with the largest possible moments. Doesn't matter. And you're rightfully so. If you guys are like, well, I would rather use the right side of that, that's great. Go ahead, do that. You'll get the same result, or at least you should. Okay. Sum of the forces y is equal to 0. Negative 20 plus 46 minus 40 minus V2. Do all that math. So note, I want you to notice something, right? If you look at this compared to the first one, right? We had 20 kilonewtons, right? Negative 20. Then we moved to the next one. We added 46, so it's 26. This is 26 minus 40, or negative 14. Notice it adds, right? And these are point loadings, and if you were to cut this someplace before 3, right? Let's say I cut this here. Let's call it 2.5, right? What if I cut that at 2.5? How does that affect everything? The shear, look, how does that affect this particular free body diagram? It makes it a little bit longer. The only two forces on there are still the 20 and the 46. So the magnitude of the shear is the same. The difference is that the moment is going to have a different value, right? And that's dictated by how far away we are, right? Remember, moment, in cases like this, the moment changes linearly, right? So we'll see what that means for us in a second. Sum of the moment, what do I call that? 2. This should be 3. Like I said, this is 3. M3, we've got plus 20 times 5.5 in this case, minus 46 times 3. And the moment for point 3 is 28 kilonewton meters. Okay. If you were to flip this and cut this at the 2 meters and look at the 14, okay, I'm not going to redraw it. You guys can redraw that on your own time if you want to check it. But I will tell you this. Let's think of thought. We'll do the thought experiment. If I were to use the right half and I'm here, okay, that moment, the magnitude of it is still 28 kilonewton meters, right? At this point, the other side, you have 14 kilonewtons 2 meters away. That's 28. That checks with what we have here. What about the shear? There's only one force. If I look at the other side, it's 14 kilonewtons. So it's the same. When you do the math, it'll flip over and be negative, right? So it checks out. So you could have done it on the other side. Again, personal preference, doesn't matter. For teaching purposes, I think it's nice to show the progression as we move along the beam. Okay, let's draw it now, right? So you guys have all of your shear and your bending and all that stuff, right? We have everything that we need here. Let's draw the whole thing out. And so I'm going to do that nice and big so that everyone can see it. So the way that I like to do this is I will redraw the entire beam full body, free body diagram, okay, to start with. So let's do that. And I'll draw it nice and big, right? So I've got my 20 kilonewton. I've got my 40 kilonewton. 46 kilonewton. 14 kilonewton. I'm going to put my distances on here. Okay. I've got everything that I need, or everything that I need, right? The next thing that I like to do when I'm drawing these is I will just make a line straight down the page to signify the start of my shear and bending moment diagram. Because what we are trying to do, again, is map this, right? And we're going to start with the shear. The shear is in kilonewtons. Please label your units. And we'll start there, and I'll put a 0 line on it. So this is going to be my 0 shear. And notice it goes straight across. I will label it as 0. And the other thing that I'm going to do is every time I have a point loading, I'm just going to make a dashed line. You'll see why in a second. And again, these are Dr. D's ways of doing this. This is not necessarily the views of Reginald Charles Hibbler. Sorry, Sir Reginald Charles. Okay, so what did we find at V1? What was the shear that we got? Negative 20? Cool. So I'm going to make a line here. I'm going to say that that's negative 20. And we said that that's constant until we get another point load, right? Okay, so it's just a straight line. That's flat. That's what constant means. All right, what about at point 2, cut 2, when that 46 kilonewtons popped, jumped up to 26. And that's going to be flat till we hit another point load. So that's 26. Okay? What happens when we hit the 40? What's the next shear? It's 14, right? So that's got to be somewhere, well, I'll say it's here. And then I'll just connect these. These are going to be discontinuous at the point loadings. That's fine. That means that at the point loading, technically you exist as a stepwise function at that point loading. That's fine. All right, so that's our shear. That's what our shear looks like throughout the entire beam. You can now tell me, no matter where I ask you on that beam, what the shear is. Okay? What about bending moment? Kilonewton meters. We'll put our 0 line in. Right below it, we're going to do the same thing. All right, what was our shear at point 1? 0. I'll make sure I put 0 here as well. Okay, what about at cut 2? Negative 50. We'll say that that's here. Negative 50. Okay, what about the next one? And finally, well, we didn't figure it out at the very end, right? But I think that we could all agree that at the very end of the beam, if you were to cut it right before that 14 kilonewtons, infinitesimally close to that 14, it would goes back to 0. And because we said that the moment changes linearly, we just connect straight line points to all of these. And there we have it. Done and done. And now you can tell me, okay, well, what's the bending moment at any point in this beam? We can figure it out. Right? I could say, hey, what's the distance away from the left-hand side at which our moment becomes 0, right? It would be this place, right? And so we would have to figure out where that is, right? But you know that it's got to be somewhere around the midpoint of the beam in there, right? Right? And that's how we do it. And that's a simple point loading. There are changes that happen when we start talking about distributed loadings, which we will talk about next class when we do an example with a distributed load. Because there are some things, some beams that get crazy. And sometimes, no. Anyway, we'll do some more examples of this next class because we've got like 5 minutes and that's all we got time for. Questions about this right now? Yeah, right. That's an excellent question. And yes, the answer is yes. We'll talk about another method for doing these next class, which is, I don't like when people say it's by inspection, not by inspection, but what is the mathematical relationship between shear and bending moment? Because there is one, right? So maybe for tomorrow, right, think about that, right? Think about, based on this particular plot that the one sample that we have, what do you guys think the mathematical relationship between shear and bending moment is? Okay. Because we'll talk about it tomorrow. Any other questions? All right. So if that's the case, I will be working on grading your guys' quizzes. We'll keep doing this next class. We'll get through shear and bending moment. We have a bunch of more examples, and then we'll move on to the next thing because can't stop, won't stop. What's up?
So, I'm working on this question.
Mm-hmm.
I'm wondering, because I'm cutting it at C, right?
Yeah.
So I'm wondering if, when I actually cut it, is the W gonna be the same or it's just 1/2? I don't think it.
So if you're cutting it at C, what did they tell you W was? It was 8. It's going to be the maximum. It's going to be, so they're telling you that at the vertex of that triangle, you have 8 kilonewton per meter. So yes, it's going to be 8 kilonewton per meter at that. For this one, yes, you're absolutely right. Like, you got to first find this guy here. I would split this into 2 triangles and create 2 forces that
Still using 8.
right. Yes. Mhm. Yes.
Or both.
So you need a SolidWorks drawing. It says you need a SolidWorks drawing, right? It needs to be a production style drawing. And so I would create one of the assembly and then I would put like of the pieces also. So both. I would say both. Yeah.
The trust and the same one
Yeah.
and.
Like one overall with everything together and then just one with the pieces that you need to manufacture. So like that. Yeah. Yeah. Sure.
It's not bad. So this is.
I'll be in my office tomorrow afternoon after class. I think I have, um, let me double check. I think I have some meeting after there, but, um, tomorrow I'm free until from 1:30 to 2, and then from 3 to 3. No, that's it actually tomorrow. You can come in the morning around, tomorrow's not good. Tomorrow's not good. I'll be on campus on Wednesday. Wednesday. Looks like I'm free from 9 to 11 on Wednesday. I'll be in my office, yeah. Sure thing.